Today we will continue to learn capacitance. As you can remember from our last lesson, capacitance is connected with charge and electric potential by formula. This formula can be written like this. Charge Q is equal to capacitance multiplied by electric potential. And today we are going to find capacitance of the ball or sphere that is made of conductor. So it is a conductive ball or conductive sphere that is surrounded by vacuum or dielectric. So a ball or sphere in vacuum or dielectric. I'll try to draw this. This is a ball or sphere. It has radius r. It has radius r. And it also has charge Q. And we want to calculate a capacitance of this ball or sphere. It looks the same on the picture, ball or sphere, and we want to find its capacitance. How to do this? We know the charge, and it is necessary to find electric potential on the surface of the ball or the sphere. How to do this? First of all, it is necessary to calculate electrostatic field around this ball. Let's try to do this. And there are two ways. To do this. First way is to use the definition of electric field intensity. So it is possible to use this formula. E is equal to 1 divided by 4 p epsilon 0. Q I divided by R minus R I in modulus to the power of 3, and R minus R I. Yes, it is possible to use this formula. It is possible, but in this case it will be difficult. And it will not be useful. Because because in this case it will be necessary to calculate triple integral because we have we have charge that is distributed in space. Charge that is distributed in space, but we can see that system this is a ball or sphere, and it has symmetry. It has symmetry. In this case, we can use second way to calculate electrostatic field, and this second way is to use Gauss law or Gauss flux theorem. Gauss law or Gauss flux theorem. And we will use integral form for electric displacement vector. As you can remember, it can be written in this way. So we will use Gauss flux theorem for electric displacement vector. Where Qs is charge inside inside a closed surface. So let's use this. How to do this? First of all, it is necessary to find left part. This is this surface integral, but in general case it is difficult to do because we don't know D, we don't know electric displacement vector. We want to find this, and the question is how to get vector D from this formula. And now we will solve this. And the second, it is necessary to find QS, a charge inside closed surface. And first of all, to do this, we have to choose some optimal form of closed surface S. How to do this? It is necessary to take into account that system has symmetry. It has center of symmetry because this is a ball, and electrostatic field always has the same symmetry as system of charges that produced this electrostatic field. So the symmetry of electrostatic field and the symmetry of system of charges that produced this electrostatic field are the same. So electrostatic field, I can draw it. Here I can draw it with these arrows. Electrostatic, it is electric displacement vectors. It can be shown like this. We know from the previous lesson that here we here we have the angle of 90 degrees, and this is vector D. And how to choose optimal surface S? How to choose this? It can be chosen. With the same symmetry as system of charges have. So we can draw surface S in this way. We can draw this in this way. And now I will make it dash. I will make it dash because I will make it dash to take into account in order to take into account the difference between a real object and something that was drawn. So I'll make this surface as I will draw it with dash line. I'll draw it with dash line. Oh, here it is dash line, and this is surface S. Why have I chosen this form of surface S? Because of in this case the directions of vector D and vector S are the same. Directions are the same. It can be it can be assigned with these two arrows. These two arrows mean that D and DS have the same direction. So I'll show this here. For example, DS. This is DS, and it has the same direction as vector D. And as a conclusion, as a result of this, we have that D dot product multiplied by DS is equal to DS multiplied by cosine the angle between vectors D and DS is equal to 0 because they have the same direction. And cosine of 0 is equal to 1. So it will be DS. It looks very similar. But in the right side we have d multiplied by ds without vectors. So expression become much more simpler than it was before. Much more simpler than it was before. And what's more? What's the next? The next we can try to calculate this integral. We can try to calculate. So according to this, we have the d multiplied by ds multiplied by ds is equal, let's make substitution, so surface integral s d ds ds. So and this is equal. Okay, do you have any questions?
No, not.
Okay, that's great. That's great. So how to calculate this integral? I have said that we have symmetry. We have center of symmetry. In our system, and the same symmetry has electrostatic field, and the same symmetry has surface S, and it means that the modulus of the vector d, or this modulus of the vector d, is the same for each element ds. D modulus of electric displacement vector is the same for every ds, for each ds. Oh, and it means that this can be written, d can be written outside the integral, because d doesn't depend on ds. Doesn't depend on ds. And here we have obtained very simple surface integral. This is very simple surface integral because maybe you can remember this from calculus. It means simple sum of all element ds. It is simple sum of all infinitely small elements ds, and it is equal to area. It is equal to area of closed surface S. So here we have d multiplied by area of closed surface S. And how to find this area? It is necessary to draw the radius. I'll sign this radius by L. It is radius of surface S. Surface S is sphere, and the area of sphere is 4p L to the power of 2 or squared L. So here we have 4p L to the power of 2 multiplied by d. It was the left part of Gauss flux theorem. And the right part is charge inside the closed surface S. This charge is equal to charge on the surface of ball. So QS is equal to Q, because all the charge is inside the closed surface. So we can substitute QS here, and we can substitute this integral here, and as a result we will obtain 4p squared L d is equal to Q, and this is equal to Q. From here we have obtained that the modulus of the electric displacement vector is equal to Q divided by 4p L to the power of 2. It is outside. It is for electrostatic field outside the ball or sphere. Inside, it is equal to 0. As you can remember from our previous lesson, the electrostatic field inside the conductor is always equal to 0. Outside we have obtained formula. It is electric displacement vector outside the charged ball or sphere. Okay, the next step is to find electric field intensity. From one of our previous lessons, you can remember. I hope so. That you can remember the formula that the dependence between electric displacement vector and electric field intensity. Epsilon 0 E. And for isotropic dielectrics, epsilon is a simple number, and because of this we can write that it is equal to epsilon 0 E without vectors. It is for isotropic dielectrics. We are learning fields in isotropic dielectrics, and from here we have that E is equal to D divided by epsilon 0, and it means that it is equal to charge Q divided by 4p epsilon 0 squared L. Okay, do you have any questions? Do you have any questions?
This is to get the electric field density, right?
This is
This
electric
E.
field intensity, E.
Okay.
So let's continue. I'll clean some space. Clean some space on my screen, and we will continue. We will continue. As you can see from this from the last formula, electrostatic field of charged ball is the same as electrostatic field for point charge. We can rewrite this. We can rewrite this in vector form. In vector form, it will be if I use radius vector. It will look like this: 1 divided by 4 p epsilon 0 q divided by modulus of vector r in to the power of 3, and multiplied by radius vector. You can see that it is the same formula as it was for point charge. The same formula that it was for point charge. And we have obtained this quite easily using Gauss flux theorem. We could have used also a superposition principle, but in that case we would have calculated some triple integral, and it would be more difficult. It would be more difficult than using Gauss theorem. Okay, now we have electric field intensity, and it is necessary to calculate electric potential, because in the formula in red frame we have electric charge in left side and electric potential in the right side of the formula, in the red frame. So let's find electric potential. According to the definition, it is equal to linear integral minus linear integral from some r0 initial radius vector of some initial point to r e d l plus phi 0. Where phi 0 is potential in initial point. And it is necessary to remember that we can choose as we want to. We can choose initial point, and we can choose the value phi 0. And it is in this case, it will be more useful or more convenient, the most convenient or the most useful to choose phi 0 is equal to 0, and r 0 we will choose infinity. And r vector, it is a radius vector of some point on the surface of the conductor, on the surface of the ball. So it is equal to the radius of the ball or sphere. And from here we have that phi is equal to minus r 0 to r e dl plus phi 0, and it is equal to minus integral infinity to from infinity to r e dl and it is equal, if we take into account this minus near the integral, we have to change places of integral limits if we take into account this minus. The integral from r to infinity e dl Okay, and how to calculate this integral? To calculate this, we have to remember that electrostatic field is always a potential field. It means that this linear integral depends only on initial and final position. It depends only on initial and final position, and doesn't depend on the way from initial to final position. So it depends only only on initial and final position and doesn't depend on the way from initial to final position. And because of this, we can choose the way from initial to final position. We can choose this way, and of course we will choose that way that we will choose such way that makes calculation of the integral makes it simplest. So we choose such way that makes calculation of integral simplest, and this way is a way with condition. So we have chosen that way. We have chosen such way that that vector E has the same direction as vector dl. We can do this because the electrostatic field is always a potential field. And because of this we can write that E dl is equal to modulus of vector of electric field intensity E dl cosine 0 and it is equal to E dl, and it is equal to E dl. It is equal to E dl. Okay, do you have any questions? No questions. No questions. So let's make substitution, and we will have that it is equal to integral from r to infinity, E dl. And this integral is much simpler than it was before. It is much simpler. Why? Because it doesn't contain any vectors. So it is not linear integral, it is simpler integral. And we have managed to do this because electrostatic field is always potential field. Because it is always potential field. So as a result, we have let's remember the formula for the modulus of electric field intensity. So it is integral from r to infinity, electric charge divided by 4p epsilon 0 L to the power of 2 dl. and it can be written as Q divided by 4P epsilon 0 integral from R to infinity d L divided by square L Okay, do you have any questions? Do you have any questions? Okay, no questions. Okay, so I will clean some space on the screen. I will clean some space. Clean some space. Clean some space. This I will move here, and okay, it is necessary to calculate. It is necessary to calculate this integral. This integral. Let's do this. Let's do this. Let's do this. Integral from R to infinity. From R to infinity, dl divided by squared L. And it is the same as limit some k tends to infinity integral from R to k dl divided by L in second L to the power of 2. Okay. And how to calculate this? How to calculate this? It is quite simple, because this is table integral dl so it is the same as integral from R to K L to the power of -2, and it is the same as -2 plus 1 -2 plus 1, and here -2 plus 1 RK, and this is the same as minus from R to K, and this is the same as -1 divided by L from R to K. and this is equal to minus 1 divided by K minus 1 divided by R. And this is equal to 1 divided by R minus 1 divided by K. Okay, do you have any questions about this integral? No questions. No questions. So here we have that it is equal to limit K tends to infinity, K to infinity, 1 divided by R minus 1 divided by K. And a number divided by infinity, is 0. So it will be 0. The second term is 0. So it is equal to 1 divided by R. 1 divided by R is 1 divided by R. And according to this, we have that it is equal to Q divided by 4 P epsilon 0 epsilon 0 R. Epsilon 0 R. This is electric potential on the surface of the ball or sphere with charge Q. Okay, do you have any questions? No questions. No questions. Okay. Okay, if there are no questions, I'll clean some space. I'll clean some space on my screen and find the capacitance of the ball. Find capacitance. From here we have that electric potential is equal to Q divided by 4 P epsilon 0 R. Epsilon 0 R. And from here we have that capacitance is equal to Q divided by phi. It is from the formula in red frame. From the formula in red frame, we have that it is equal to 4 P epsilon 0 R. Epsilon 0 R. Okay, do you have any questions? So we have obtained that capacitance of charged ball of charged ball is equal to 4p epsilon 0 r. Epsilon 0 r. And let's try to use this formula. For spheres that have radius the same as the radius of our planet. Radius of the Earth. Radius of the Earth is equal to approximately 6,400 kilometers. 6,400 kilometers. And if we substitute this here for vacuum, epsilon is equal to 1, we will get that C is equal approximately to 700 farads. 700 farads. No farads, sorry. No farads, microfarads. Microfarads. 700 microfarads. It is very small. It is very small capacitance for such a big system. And so the question is how to make electric device that has small size and big capacitance. This is the first question, and the second question is that the capacitance of conductor depends on other conductors near it, and it depends on electric charges near it. So the second question is how to make a device with capacitance that doesn't depend on neighbor conductors or neighbor charges. And this device is known as capacitor. Now I will type the definition. I will type the definition. Capacitor. Capacitor is an electronic device. Is an electronic device that stores electrical energy. In an electric field. By accumulating electric charges by accumulating electric charges on two by accumulating electric charges onto closely spaced surfaces that are insulated from each other. That are insulated from each other. Oh, quite a long definition. But you can see it here. This is a capacitor. This is a capacitor. And this is capacitor. And according to this definition, you can see that capacitor consists of two conductors that have form of surfaces, two conductors, two conductive surfaces, and some dielectric or vacuum between them. And because we have two conductors, the charge of capacitor is equal to, according to the formula, is equal to capacitance multiplied by electric potential of first conductor minus it will have minus because the surfaces has charges, has positive and negative charges, has charges with different signs. Phi2. And this is equal to C Phi1 minus Phi2. And this is equal to C multiplied by U. So Q is equal to capacitance multiplied by U, where U is potential difference or voltage. U equal to Phi1 minus Phi2. U is difference of potentials or voltage or voltage. Or voltage. Okay, do you have any questions? No questions. No questions. So let's clean the screen. Let's clean the screen. Let's clean the screen and make some changes on it. The definition of capacitor and And here Gauss flux theorem or Gauss law, and let's try to find let's try to learn some typical capacitors. There are three most common types of capacitors. They are a parallel plate capacitor, cylindrical capacitor, and spherical capacitor. The simplest is parallel plate, the simplest and the most common. Capacitor is a parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor. What is this? What is this? It consists of two conductors that have form of planes. Two conductors that are plane surfaces, and between these surfaces is vacuum or air or some dielectrical media or some dielectric. Here we have charge plus Q. Here we have charge minus Q. Area of plates is equal to S. Between these plates we have electrostatic field. We have electrostatic field between plates of capacitor. And this field can be signed as, for example, E or D. The direction is the same, and relative permittivity is E, and the distance between plates is equal to D. This is the distance between plates of capacitor. And the question is how to find its capacitance. How to find capacitance of parallel plate capacitor. We'll use Gauss flux theorem again. And the situation is the same as capacitance of sphere or ball. The first step is to choose the closed surface. We should choose this according to the symmetry of the system. The system has plane of symmetry, so it is necessary to choose the surface S with the plane of symmetry. So we have we can choose the surface S in this way. I'll make it dash. I'll draw it with dash line in order to make difference. In order to make difference between drawn and real object. Between drawn and real object. Surface S has area S and S. Okay, and let's calculate the integral in the left side of Gauss law. The situation is the same as it was. The situation is the same as it was for the capacitance of sphere. So the integral is ds is equal to integral ds without vector, because we have chosen appropriate surface, and d doesn't depend on ds, so it can be written outside the integral. It can be written outside the integral. S d s, and this is equal to ds. This is equal to ds. This is equal to ds. Okay, do you have any questions? Do you have any question? Vector ds is somewhere here, for example. ds, and ds has the same direction as vector d. Okay, and the charge qs, charge inside the closed surface S, charge is equal to Q. This is equal to the charge of left plate of parallel plate capacitor. So QS is equal to Q. Okay, let's make substitution. So ds is equal to ds is equal to Q. Is equal to Q. And according to this, d is equal to Q divided by S. Q divided by S. Okay, let's find electric field intensity. Electric field intensity. We can remember from our previous lessons that electric field displacement vector, electric displacement vector, or electric induction vector is equal to epsilon 0 E. And when dielectric is isotropic, or vacuum, it can be written like this. D, without vectors. Without vectors. And and because of this, we have that E is equal to Q divided by epsilon 0 S. Epsilon 0 S. Okay, do you have any questions? Do you have any questions? No questions. No questions, okay. If there are no questions, I have to clean some space, some place. I have to clean some place on the screen. I have to clean some place. I need this formula, and it is necessary to calculate the difference of potentials or voltage. How to do this? How to do this? It can be done. It can be done by the formula. U voltage is equal to integral from the distance between plates is d. So it from 0 to d vector E dl. Electric field is a potential field. So because of this, we can write that it is equal to integral from 1 to d E dl without vectors. And it is equal to integral from 0 to d q divided by epsilon 0 s dl and everything inside the integral doesn't depend on L, so it can be written outside the integral. S from 0 to d dl, and this is equal to q multiplied by d divided by epsilon 0 s. Epsilon 0 s. So we have that voltage is equal to q d divided by epsilon 0 s, and this is equal to this is equal to E, electric field intensity, multiplied by the distance between plates of parallel plate capacitor. Okay, do you have any questions? No questions. No questions. So in this case, we can calculate that capacitance of parallel plate capacitor is equal to U, charge divided by voltage U, and this is equal to epsilon 0 S divided by D. Divided by D. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay. Okay, so we have obtained a formula for capacitance of parallel plate capacitor. So we can write that for parallel plate capacitor, parallel plate capacitor for parallel plate capacitor, the capacitance is equal to epsilon 0 S is area of plates, D is distance between them, and okay, any questions? Any questions? No questions. Okay. That's quite good. That's quite good. If there is no questions, I hope that everything is clear. I hope that everything is clear. And I will erase this. And the next type is cylindrical capacitor. The conductors or surfaces of the cylindrical capacitor are coaxial cylinders. Two coaxial cylinders, one inside the other. Two cylinders, conductive cylinders, one inside the other, and they have the same axis. here you can see it from this side. Two cylinders, two conductive cylinders, one inside the other. One inside the other. One inside the other. The axis of symmetry. Axis of symmetry. And the radius of small cylinder is R1, and the radius of the bigger cylinder is R2. Is R2, and the height of the cylinder height of the cylinder is equal to h. Is equal to h. Height of the cylinder or cylindrical capacitor is equal to h. And let's have a look at the other view of this capacitor. Other view from on its base. The base of capacitor is a circle, or base of cylinder is a circle. So it can be drawn like this. It can be drawn like this. This is R1, R1, R2, R1, R2, R2. The charge here is plus Q, and the charge here is minus Q. There is no difference if we change places of positive and negative charges. The result will no change if we change places of positive and negative charges. And let's use Gauss flux theorem. The first step is to choose the surface S. In this case, the surface S is also a cylinder. Is also a cylinder. Cylinder that is coaxial. That is coaxial with capacitor. Coaxial with capacitor. And I'll make the surface S with dash line. With dash line. I will make it with dash line. And it has radius L. Radius L. Okay, let's use Gauss flux theorem. Let's use Gauss flux theorem. The surface integral. The surface integral is equal to d. It can be it can be written as a result of appropriate choice of surface S, because we have chosen surface S in appropriate way. We can rewrite this integral without vectors, and we can put d outside the integral. And this is S d S, and this is equal to d S, and square of side surface of the cylinder is 2p 2p L H multiplied by d, and the charge inside the surface S is equal to charge of internal cylinder. This is plus Q. So we can substitute this in Gauss law, and according to this we have 2p L H d is equal to Q. Electric displacement, the modulus of electric displacement vector is equal to, it is d equal to Q divided by 2p L H. 2p L H is divided by 2p L H. And we can find that d electric displacement vector is connected with electric field intensity by formula. And because of this, we have that d is equal to epsilon for isotropic dielectrics. And from here we have that E is equal to d divided by epsilon 0, and this is equal to Q divided by 2p epsilon 0 L H. Okay, do you have any questions about this? No questions. No questions. So I will clean some space. I will clean some space to free some place on the screen. And let's continue with cylindrical capacitor. Potential difference of potentials. Voltage is equal to integral from R1 to R2 E dl, E dl, and it is equal to similar integral without vectors because electrostatic field is potential field. E dl, and it is equal to integral from R1 to R2 Q divided by 2p epsilon epsilon 0 LH d L, and it is equal to Q divided by 2p epsilon epsilon 0 H integral from R1 to R2 dl divided by L. Okay, let's calculate this integral. Integral from R1 to R2 dl divided by L. It is equal to natural logarithm of modulus of L from R1 to R2, and it is equal to natural logarithm of R2 minus natural logarithm from R1. Here I have taken into account that R1 and R2 are radiuses and they are positive. And because of this, there are no modulus. And it is equal to logarithm of R2 divided by R1. So we have that this is equal to Q 2p epsilon epsilon 0 H multiplied by natural logarithm of R2 divided by R1 and this is voltage of cylindrical capacitor, and let's clean some place, and we have
Teacher,
yes,
why here? Here. Call R2 divided by R1.
because there is a property for of logarithm. According to this property, natural logarithm, or maybe not natural, every logarithm, for example, logarithm with base a of b minus
Okay, teacher, I understand. Here is ln, not ln. Okay, I understand.
yeah, the difference of logarithms is equal to logarithm of
I understand.
yes, of one argument divided by the other argument. Okay, it is necessary to finish, and I will write that. So we have obtained that voltage is equal to this, and we can substitute this here, and for the cylindrical capacitor, capacitor with homogeneous dielectric has capacitance 2p epsilon 2p epsilon 0 h divided by natural logarithm of R2 divided by R1 This is for cylindrical capacitor, and for spherical capacitor I will not prove this formula. I will only write this. Because the proof is similar to proof for cylindrical capacitor. So spherical capacitor has capacitance C is equal to 4p epsilon 0 R1 R2 divided by R2 minus R1 R2 minus R1 minus R1. Okay, that's all for today. Do you have any questions? No questions. Okay, so thank you for your attention. I hope to meet you tomorrow.
See you tomorrow, teacher.
Yes, okay,
Okay,
thank you.
teacher, see you tomorrow.
Okay.